In this video, we're going to go through alkanes in even more detail. Remember that alkanes are saturated. They have only single bonds. And remember that carbon has to have 4 bonds. So we're going to learn how to write alkanes and how to name them. So alkanes are hydrocarbons that contain only carbon-carbon and carbon-hydrogen single bonds. They are formed by a continuous chain of carbon atoms. They are named using the International Union of Pure and Applied Chemistry system, also known as the IUPAC system. All alkanes have a name that ends in ANE, so that is the suffix, ANE. We are going to use different Greek prefixes to name carbon chains with 5 or more carbon atoms. So here are the names for the first 10 alkanes. Methane has 1 carbon. Ethane has 2 carbons. Propane has 3 carbons. Butane has 4 carbons. Once we reach 5 carbons, that's where we will use the Greek prefixes. Pentane for 5, hexane for 6, heptane for 7, octane for 8, and nonane for 9, and finally decane for 10. Now there are 3 different ways in which these alkanes are represented. We have our molecular formula, where carbon comes first, and then we have hydrogen. Now, here I have N. So when you have an alkane, if you have N carbons, then you have 2N plus 2 hydrogens for an alkane. Again, this is a saturated hydrocarbon. Next, we have the condensed structural formula. So here you can see that the bonds only between the carbons are indicated, and you have the hydrogens directly bonded to each carbon. This third representation is called a line angle formula. And what you can see is that it is an extreme shorthand of how to represent these hydrocarbons. Now, at the end, I'm going to draw propane. What I want you to see is that each point represents a carbon. What is not drawn in is the hydrogens. So the hydrogens are implied. So let's look at this table again. I want you to realize that these line angle formulas are slightly offset. So there's no line angle formula for methane. This first one should be ethane. And then you have propane. And then butane, which has 4 carbons. And each carbon is at the point. And the hydrogens are implied. So here at the end, you would have 3 hydrogens. Here in the middle, you would have 2 hydrogens. So just realize with these line angle formulas, they show the carbons at each point, but the hydrogens are implied. We're going to use these line angle formulas to represent different organic structures. So from a rule perspective, we need to remember that the carbons are at each point. The hydrogens are not drawn in. When bonded to carbon. But they are implied. All right, so keep this in mind. This is setting the foundation for drawing organic structures. And you can just look here. This is decane. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons there. And on each of those carbons are hydrogens. On the ends, you'll have 3 hydrogens, and then in the middle, at each of those points, you'll have 2 hydrogens. When you have a condensed structural formula, each carbon atom and its attached hydrogen atoms are written as a group. The subscript indicates the number of hydrogen atoms bonded to each carbon. The condensed structural formula of butane has 4 carbon atoms. So you can just see this enlarged from the table. So this is the condensed structural formula. You're going to draw in the bonds for the carbon-carbon bonds. And you're going to use subscripts to indicate how many hydrogens are bonded to each carbon. So if I was to draw this out in expanded form, you would see the individual hydrogens bonded to each carbon. So this would be that expanded form. We saw this in the first video. So here again, this is just emphasizing that difference between the expanded and the condensed structural formulas. So now again, we're going to just review how to write these skeletal formulas. It takes a little while to get used to. So alkanes can be represented by that molecular formula. So here we have butane, so that would be C4. Now remember, to determine the number of hydrogens, you just use that 2n plus 2. So it would be there, the number of hydrogens here would be 10 because there's 4 carbons. So 2 times 4 is 8 plus 2. For a saturated hydrocarbon or an alkane, we need to have 10 hydrogens. We can then use our line angle formula, which shows the carbon skeleton. So each point represents a carbon. We do not draw in the hydrogens that are bonded to each carbon. They are implied. In our first video, we saw that alkanes can be represented by a molecular formula, which doesn't really give a lot of information. It just tells you how many carbons and hydrogens you have. We can also use a ball and stick model. We can use an expanded structural formula where we show every bond. We can do a condensed structural formula where we only show the bonds to carbons and we have the number of hydrogens indicated by a subscript, or we can use our line angle formula. So this table is showing you the different structural representations for butane, which is C4H10. Now here, I just want to bring your attention, it doesn't matter which way you start your line angle formula. You can start with the carbon down, or you can start with the carbon up. So given the following expanded structure, let's provide the molecular formula, the condensed structural formula, and the compound name. So if we count, we will see that we have 5 carbons here and that we have 12 hydrogens. So 1, 2, 3, 4, 5 carbons. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So our molecular formula is C5H12. For our condensed structural formula, we are only going to show the carbon-carbon bonds. So it is going to be CH3, CH2, 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 CH3. So we have our 5 carbons, 1, 2, 3, 4, 5, and we have our 12 hydrogens. 3 plus 2 is 5, plus 2 is 7, plus another 2 is 9, plus the final 3 is 12. The compound name will be pentane. Now let's write the condensed structural formula for the following 2 alkanes. We have ethane and heptane. We know that ethane has 2 carbons, so it'll be CH3-CH3. For heptane, there are 7 carbons. So we have 1, 2, 3, 4, 5, 6, 7 carbons in our chain. Now what we're going to do is we're going to look at cycloalkanes. Cycloalkanes are cyclic alkanes. They are going to have 2 fewer hydrogen atoms than the open chain form. We are going to name cycloalkanes by inserting the prefix cyclo before the name of the alkane chain with the same number of carbon atoms. So let's look at our example here. Propane is C3H8. There are 3 carbons. If we have 3 carbons in a ring, we will say cyclopropane. So notice that there are 2 fewer hydrogens here. Here are some formulas of some common cycloalkanes. We have cyclopropene, which has 3 carbons, cyclobutane, which has 4 carbons, cyclopentane, which has 5 carbons, and cyclohexane, which has 6 carbons. You have your condensed structural formulas here and your line angle formulas shown at the bottom. Let's give the IUPAC name for each of the following compounds. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons, so this will be octane. Here we have a ring. We have 1, 2, 3, 4, 5 carbons, so the parent name or the root name will be pentane, and because it's a ring, we have to add cyclo. So it's cyclopentane. Here's another learning check where we're going to look at nomenclature. So we have 4 carbons in the first example. This will be butane. We have 3 carbons in the second example. The parent name will be propane, but it's a ring, so we have to add cyclopropane. Let's count this chain here. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons. This will be an octane. And then we have another ring. 1, 2, 3, 4, 5, 6. So the root name is hexane, and we have to add cyclo in front. In addition to these linear chains, we can have alkanes with substituents, where instead of having just a straight linear chain, we may move a methyl group to a different carbon. This is known as a substituent. It is a branch point attached to a carbon chain. We are going to learn about these compounds in the next several slides. We are going to learn about different compounds known as isomers. There are many different types of isomers. So when we have an isomer, we have the same molecular formula. The first type of isomer that we're going to look at is a structural isomer or a constitutional isomer. What this means is that we have the same molecular formula, but the atoms are going to have a different arrangement. So where you have a different connectivity or constitution. Or structure. All right, so again, the same molecular formula. So here we have C4H10. Here we have C4H10. But you can see that they are connected differently. And when they are connected differently, this leads to different properties. Let's do a learning check. We're going to draw 3 possible structural isomers for pentane. What you want to do is you want to start with the linear chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now what I'm going to do is I am going to remove the last carbon from the chain and make what is known as a branch point. So now I'm going to have 4, 1, 2, 3, 4, and then I'm going to add that 5th carbon. So let me just number for you again. 1, 2, 3, 4, and then there's the 5th. All right, so now for the next structural isomer, I'm going to remove carbon 4. So now I'm only going to have a chain of 3, 1, 2, 3, and I am going to put 4 and 5 on that middle carbon. So 1, 2, 3, 4, 5. What I'm going to do is I'm going to redraw this chain here. And I want you to realize that these 2 molecules are the same. That if you were to flip the bottom one over and then rotate it, you would get it to superimpose. So those are exactly the same. So these are the 3 possible structural isomers of pentane. So what you have to realize is you're going to start with the long chain. Then you're going to remove a carbon from the end and make it a branch point. So this would be a branch. And then you're going to shorten the chain again and draw another branch. And once you realize that there's no redundancy in your structures, then you stop drawing. So we can see that we have 1, 2, 3 different types of structural isomers or constitutional isomers of pentane where the carbons can be arranged differently. So just in case you can't interpret my chicken scratch, you can see those line angle formulas here, and you also have condensed structural formulas for each in case you have trouble visualizing the line angle or bond angle formulas. When we go through this process of drawing the different constitutional isomers and you remove a carbon from the end of a chain and make it a branch point or a substituent, that carbon now becomes known as an alkyl group. So we're going to have to apply a different strategy when naming that compound. So again, if you have a compound with C4H10, but you only have a linear chain of 3, it's not going to be butane. Instead, it's going to have a different name. And this group, this carbon that we removed from the end, is known as an alkyl group. And it is going to be named as a substituent with the -il ending. We can also have different types of substituents in addition to alkyl groups. If you have a halogen that's attached to a carbon chain, it'll be known as a fluoro, chloro, bromo, or iodo group. We're going to look at some examples of this to make it a little bit more clear. So, similar to those parent names that we looked at when we started naming alkenes, when we have an alkyl group, we're going to use similar parent names. So, for 1 carbon, it is known as a methyl group. 2 carbons are known as an ethyl group. 3 carbons, you can have different types of names. If it is just a linear chain of 3, it is a propyl group. If you have a branch, so see here where you're attached through that middle carbon, that is known as an isopropyl group. If you have a linear chain of 4 carbons, that is a butyl group. If you have a substituent coming off of the chain where there's then this branch, it is known as an isobutyl group. And then for the halogens, fluorine is fluoro, chlorine is chloro, bromine is bromo, and iodine is iodo. Let's look at this example, this learning check. What I'd like you to do is not pause the video, but actually go through and listen to me as I do this. Okay. Let's count the longest continuous chain of carbons that we have. If I were to count here, I would see that I have 1, 2, 3, 4 carbons in a row. And then it would look like we have a branch point. But I could also count where I have 1, 2, 3, 4, 5 carbons, and then here would be my branch point. So the blue way is the correct way to number the carbon chain because it's the longest continuous chain of carbons. When we have a chain of 5 carbons in a row, that is a pentane. Now we have to identify the substituents. If we look, we have a chlorine and we have a methyl group. When identifying substituents, you want to give them the lowest possible numbers. So if I were to keep my chain numbered as I have in blue, I would have a 2-chloro and a 3-methyl. Now, I'm not trying to confuse you, I just want to show you. If I instead said 1, 2, 3, 4, 5 carbons, then that would make this a 3-methyl and a 4-chloro. That is incorrect. Okay, again, you want them to have the lowest possible numbers. As we learn about different types of substituents, also known as functional groups, what we are going to see is that as we build our repertoire of organic molecules, these substituents or functional groups will have different priorities. So a halogen and an alkyl substituent are the same priority. So what you just need to do is assign each one the lowest possible number. And so we have 2-chloro, 3-methyl. Now when we assemble the name, we are going to go in alphabetical order of the substituent. So C will come before M. So the name is going to be 2-chloro, 3-methyl pentane. Right. So the steps for doing this are going to be to identify the longest continuous chain of carbons. That is going to form the root or parent name. In this case, it was pentane. Then we are going to identify the substituents and assign them the lowest possible numbers. Then what we are going to do is we are going to alphabetize when assembling the name. Okay. I know this seems very complicated. We're going to practice it. And I promise you, I'm not going to give you anything overly complicated. I just want you to get a flavor for naming these compounds. So these next couple of slides are just stepping you through what I did. All right. So again, it's using the table format that we used for all of those calculation problems. The longest chain is 5 carbons. Then you are going to identify the substituents, and you are going to give them the lowest possible numbers. So it's 2-chloro, 3-methyl pentane. If you have a cycloalkane with a substituent, you're going to identify the carbon in which has the substituent. If there is just a single alkyl group or halogen, no number is needed. So here we just have the one substituent, and it is an ethyl group, so it's ethyl cyclohexane. So in addition to being able to name a structure, we're going to have to be able to draw a structure when given the name. So if we have the IUPAC name 1-chloro, 1,2-dimethylheptane. Okay. What this means is that there are 7 carbons in the chain. That's the parent name or root name. So what you will do is draw a chain of 7 carbons. 1, 2, 3, 4, 5, 6, 7. If you look, 1 indicates that there is a chlorine on carbon 1. This 1,2-dimethyl, what this means is that on carbon 1 there is a methyl group, and on carbon 2 there is a methyl group. And that is it. That is all there is to this name. Again, I'm not going to keep anything overly complicated. When you have 2 of the same substituent, you need to designate the number, and then you use di. If there's 3 of them, it would be tri. If there's 4 of them, they'll be tetra. So let's draw the condensed structural and the line angle formula for 3-bromo 1-chlorobutane. If we dissect this name, the parent will have 4 carbons. So that's 1, 2, 3, 4. This means that there's a 3-bromo group. So here's your bromine. And then there is a chlorine on the first carbon. If I were to draw the condensed formula, it would look like this. So you can see the condensed structural formula written here, where you have a Cl, CH2, CH2, a CH with a Br, and then a CH3. So this is just stepping you through. Here is your linear chain. Here's your 4 carbons. Then we are going to put in our heteroatoms, our halogens. So then we add our hydrogens in. And to the bond line structure, we add in our halogens. So let's name each of the following alkanes. If we number, we have 1, 2, 3, 4, 5 carbons here. So the parent name will be pentane. The chlorine is on position 2, so it'll be 2-chloropentane. Here, let's look for the longest continuous chain. 1, 2, 3, 4, 5 would be the longest continuous chain. There's a methyl substituent on carbon 2 and a methyl substituent on carbon 3. So this would be 2, 3. There's 2 of them, so we have to use the di. Methyl pentane. I just want to note, and I don't think you'll have any examples of this, the hardest examples are going to be in the homework just so that you can practice it. But on any kind of an examination, I will keep the examples fairly simple. But when you're alphabetizing, you do not count the di in your alphabetization. So what this means is that if you have something like a fluoro substituent and a methyl substituent, and there's 2 methyl substituents, you're still going to alphabetize by the M. So again, I just want to give you different ways of visualizing this so that you can see the longest continuous chains highlighted in red. Then where we put our substituents, it's a 2-chloro and a 2,3-dimethyl, so that when we assemble both names, one is 2-chloropentane for A and B is 2,3-dimethylpentane. Now, after we've learned how to name alkanes, we're going to look at their properties. When we look at alkanes, we are looking at only carbon-hydrogen single bonds. Alkanes with 1 to 4 carbons are gases at room temperature, and they are widely used as heating fuels. Alkanes with 5 to 8 carbons are highly volatile liquids at room temperature, and they also make useful fuels. So you have pentane, hexane, heptane, and octane. Let's just discuss the physical state of these alkanes. There are no polar bonds when we have just carbons and hydrogens. They have very similar electronegativities. So your alkanes are nonpolar molecules. So the only types of intermolecular forces that are present are those dispersion forces. If you remember from that chapter, the strength of a dispersion force increases as we increase the molecular mass. So when you only have 1 to 4 carbons, you don't have a lot of molecular mass. The molecules do not really interact with each other, and we have gases, so the molecules are very far apart. As we increase the number of carbons, we can increase the strength of those dispersion forces because we have an increase in molecular mass. And now we have very highly volatile liquids at room temperature. What I mean by volatile is that they actually evaporate quickly. They have very low boiling points. When we get to alkanes with 9 to 17 carbons, we have liquids that have higher boiling points. They're found in motor oils, mineral oil, and kerosene. And the reason is because we have these extensive chains with a high molecular mass that can have more London dispersion contacts. So we're being held tighter together. Those intermolecular forces have increased, and that's what's affecting the boiling point. Alkanes with 18 or more carbons actually start to form waxy solids at room temperature. All right, so think about butter. Butter is a saturated hydrocarbon. You just have carbons with carbon-hydrogen single bonds, and you have very long carbon chains. And as a result, you can have this semi-solid or waxy solid state. So again, alkanes are nonpolar. They are insoluble in water. They are actually less dense than water. They are flammable in air, and they are found in crude oil. So if there's an oil spill in the ocean, the alkanes in the crude oil, they don't mix with the water, but they form a layer on top of the water and float on the surface. As far as organic compounds go, alkanes are fairly unreactive. They have strong carbon-carbon bonds. They will react with oxygen gas to make carbon dioxide and water. They release energy when the carbon-carbon bonds are broken in these combustion reactions. So here, if you have methane in the presence of oxygen gas and you add heat, you will produce carbon dioxide, water, and energy. So remember when we went through our chapter of reactions, we looked at combustion. So alkanes react through these combustion type reactions. So you can see here, butane is used in portable burners. It undergoes combustion and produces enough energy to cook food. And you can see here, C4H10. And it's a gas, and we find it in these canisters that we can take camping with us. And in the presence of oxygen and then a flame, we can produce carbon dioxide, water, and heat. So let's do a learning check. We have propane, and it's a fuel that's used in barbecues. Let's write a balanced chemical equation for the complete combustion of propane. All right, so if we remember from our combustion reactions, here's our propane, here's our oxygen. The products are always going to be carbon dioxide, water, and heat. First, balance your carbon atoms. There are 3 carbons on the left, so we need to have 3 carbons on the right. Now let's look at our hydrogens. There are 2 hydrogens on the right and 8 hydrogens on the left, so let's put a 4 in front of the water. Let's look at our oxygens. We have 6 oxygens when we do 3 times 2, so there's 6 oxygens here, and then there are 4 oxygens there for a total of 10 oxygens, so we simply need to put a 5 in front of the O2. And now we have our balanced equation with 3 carbons, a total of 8 hydrogens, and a total of 10 oxygens. So this slide just summarizes what I did. So from the alkane perspective, you need to know how to name them. You need to know how to draw a structure from the name. You need to know about their physical states, which ones are gases at room temp, which ones are liquids at room temp, and which ones form waxy solids at room temp. And you need to understand why that is the case. And you need to know about combustion reactions. But that should just be review because we already did combustion reactions in Chapter 7.